Okay, okay, here we are. So, hello everyone, and today welcome back to our live work. And yes, today we're gonna be still talking about practice problem practice problem K from 3.091. And yes, unfortunately, I I just made some mistakes, but yeah, we should be able to fix this pretty quickly. So let's just go and straight into the questions here. So the first one that, so yeah, the first thing that I just made a mistake on is let's see which one is it? The pH of 8. We have done that. Now let me just check my book. Um. Okay. So that's already correct one. And that's for number 8. Number 9. Wait, where's number 9? It's 1.34. Yep. And then for number 10, that's already correct. For I'm just checking this one by one just in case. So yes, number 11. I made I made a like yeah, I made a mistake here. So yeah, basically what is the common ion effect? It is just basically something from Le Chatelier. It is basically stating if one ion gets larger in larger in concentration, that means the other ion will actually decrease its concentration. That is just basically its principle. So yeah. So yeah, it is um so the more concentrated the solution is with one ion, the other will decrease. And yes, and yeah, is it similar? The answer is yes. And then explain your answer. Well, yeah. It's oh well, yeah, because like yeah, for buffers they just actually yeah, yes. Yes, because buffers uses this fact. So yeah. Um, is this effect similar to also yes? So yeah, according to my logic, it should be yes, but I don't know how to. Yeah, but I don't know how to actually explain it. Yes, explain your answer. Um, how should? Let's see here. Well, yeah, actually, from my book, it's just actually just the same with the one on the top. So yeah, and yeah, that's because of the ion is actually pretty much the same. So yeah, so basically, when the ion actually increases, the other ion goes and decreases. No, sorry, deconcentration. But yes, it's just basically just tending towards somewhere. So yeah, that's just basically that. But yes, I'm so sorry if my if my if my if my explanation is not that clear. And yeah, and yeah, for this one here, we only need to find what is x here. So yeah, so yeah, the first one is 9.68. The other one is this guy, and then the third guy would be that guy. So yeah, that's just basically quicker for number 13. Well, let's see here. Number 13, I did this correctly, so good. And yeah, last time we actually just got stuck at problem 14. And so, uh, and so yeah, and so yeah, all I did was I actually just so yeah, I just do the same thing. I just try to figure out what should it be. And so yeah, the first thing that I just found out is that the concentration of silver nitrate is 3.75 times 10 to the power negative 4. So yeah, we basically know what's the concentration of silver. In this case, it's 2.14. So yeah, let me just go ahead and just remove this bottom side here. So yeah, the concentration of Ag plus here equals to... No, wait, sorry. Wait, what? Yeah. Because like yeah, you're just basically just dividing it with the total. So yeah, it's 2.14 times 10 to the power negative 3 molars. Okay. And yeah, by the way, this one here at the top here, that is in moles. And then we also found out how many sodium sulfate are there, which in this case we found it to be 4.2 times 10 to the power negative 4, which would mean that the SO42 minus here would be, let's see, would be when you just divide it by the volume, it would be 2.4. Oh, something went wrong. Something really went wrong. Huh. Okay, that's weird. Yep, there you go. 2.4 times 10 to the power of negative 3 molars. And so and so all you need to do is to just define what is the Q in this case. So yes, basically Q actually represents the like yeah for the like the like oh wait no sorry for the Q here is is to actually to find out how much no sorry this Q here is basically related to the KSP. So yeah, we just need to find out what the Q is. The Q here in this case here would equal to the concentration of Ag plus squared and also SO42 minus. And so when we just actually just plug in the numbers, what you get is 1.1 times 10 to the power of negative 8 molars, which is actually less than the KSP, which is 1.2 times 10 to the power of negative 5. So this would mean that it doesn't precipitate. But if but if it actually precipitates, you want to try to make sure that it would be balanced. No, sorry. But if it precipitates, you just need to find the concentration of Ag plus and SO42 minus, and for the KSP. And yes, by the way, the Ag plus and the SO42 minus should have the same concentration. It should. Well, actually no. It should be like around 4x cubed. Yeah. So yeah. Basically all you need to do is to find the concentration first, and then after that you can just divide no sorry multiply it by the total volume to get the amount of moles, and then you can just convert it into the mass. So yeah, that's basically it. So now we are going to number 15 here, the maximum solubility. Here we go. Given 300 milliliters of a solution that is 0.056 molars in lithium nitrate, what mass of solid sodium carbonate can be added before precipitation occurs, assuming that the volume of solution does not change after adding the solid? KSP equals to 8.15 times 10 to the power negative 4 for lithium carbonate. Okay. I guess this question is pretty similar to the one before. So yeah, we can just basically first and just do it. Yeah, we can first just do it. And unfortunately, I don't have my phone, so yeah, I'll just use my tablet just to check on YouTube. Let's see. Um, let me just let me just manage this first. So yeah. So yeah, first things first, the amount of lithium nitrate. Oh wait, no, sorry. The volume doesn't actually change. So yeah. So yeah, we don't really need to care about the change in the molarity. So yeah. Um so okay. So to try to find the maximum solubility, you want to know that Q would equal to KSP, which would equal to 8.15 times 10 to the power of negative 4. And yes, and yes, for today the Q would be, and yes, sorry, for this question the Q would be, let me just actually open up an incognito tab, there we go. So this would equal to the concentration of lithium plus squared and the concentration of carbonate 2 minus. Um and then let me just go to YouTube first. There we go. Um Let me just try to find my channel. Ah, I know. I know, like, yeah, there's yeah, I know, like, yeah, my channel, there's like this other thing on Jomat, which is basically something pretty weird. Oh well. Uh, can I see the chat? Unfortunately, I can't. Oh, yikes. Well, yeah. So, so yeah, basically, this is basically the method that I'm gonna be using. Um, that would be the lithium carbonate. Okay, so yeah, first thing first, that we know that lithium plus NO3 nitrate. Wait, sorry, nitrate, is it NO2 or wait, sorry, let me just check just in case. I believe it's NO3, which it is. Okay, good. So it's lithium nitrate would equal to lithium NO3, and then after that, so yeah, this is lithium plus. That would that that would result. There we go. And then sodium carbonate is Na plus carbonate, which is CO3 2 minus. So that means that you need two of those to make NaCO3. Um. Okay. Um. This is where my problem solving comes in. Okay. Okay. So yeah, basically all you need to. Oh wait, no, sorry. So yeah, before this, we can just figure out the concentration of lithium plus and also nitrate. But yes, we don't. But yes, we don't really need to care about the lithium. And yes, the concentration of the nitrate would equal to the concentration of lithium. So yeah, that's the concentration. Oh wait, no, sorry. We require the lithium. Oh wow. I am really the best at. I am literally the best at doing this, at doing these questions. So yeah, you put the lithium there, and then after that you need to calculate the other guy. So yeah. And then for the carbonate, we can just assume that to be X. Yeah, yeah, yeah. Why not? So yeah, we can just assume that to be X molars, and yes, the result would be. So yeah, the amount of sodium carbonate would be also X, which is pretty good. So yeah, all we need to do is to just try to find out what 0.056 squared multiplied by X is. But yes, we just need to just move the thing around. So that's why I'm gonna pull out my calculator, my Desmos scientific calculator, because I don't really want to actually my grab my calculator because it's too far away. So yeah, if you don't have any scientific calculator, you can just use Desmos. So let's just do this. 8.15 times 10 to the power of negative 4. No, 8.15, 8.15. There we go. 8.15 multiplied by 10 to the power negative 4. Divide the number. Uh, divide the number by 0.056 squared. And that should be your x. Which in this case, the x here would equal to 0.25, 26 molars. Yeah, pretty close. And so that's the concentration of sodium carbonate as well. And so with this, we can just put in. No, sorry, we can just multiply it. So yeah, we can just multiply it by the volume, which in this case is 0.3 liters. So when we just multiply it, answer multiplied by 0.3, you'll get 0.078 molars. No, moles. Which in turn you can just multiply it by the what do you call it? By the molar mass of sodium carbonate, which you can just actually just look up. And yeah, by the way, this is Na2CO3. So get your periodic table and just plug in the numbers, which I won't be bothered by the decimals. So yeah, it's like 23, 46, 46 plus carbon, which is 12. So that's 68. Yeah? No, sorry. No, sorry. It's 46 plus 12. 46 plus 12, that's 58. 58 plus 48, that's 106. Yeah. So yeah, we just need to multiply the thing by 106. We multiply the thing by 106. And that would get us the grams. So all we need to do is to add in 8.26 grams. There we go. And yeah, I should have actually just because like yeah, this is not really about acid and bases anymore, but instead this is all about equilibrium. So yeah, you know what? Who cares? Oh wait, never mind. We also have the acid and base here. So number 16. Identify the conjugate. The conjugate. the conjugate acid base pairs in the following reactions. Oh wait, actually before that, let me just open up my YouTube settings. I know that the frames would drop significantly, but yeah. I am just checking just in case if there is any chat relating to this or some other thing. So yeah, while waiting, we can just actually go ahead and just check this out. So yeah, actually I don't need this guy anymore. So yeah, here we go. Number 16. Identify the conjugate asset base pair in the following reactions. Okay, so yeah, the first things first that you need to realize is that yeah, acids wants hydrogen as bases try to get rid of it. So yeah, we basically have a donor and we also have the receiver. The donor would be someone who wants sorry. The donor wait no sorry. Yeah. The donor is an acid while the receiver is basic. I believe it's like that. Yeah. Yeah, because yeah. So yeah, let's just let's just try that first. So A part 1 would indicate that Hi here would be acid because it gives a proton to the H2O. Part 2 would be a H2O would be a base. No. There's no such thing as those. Okay, and then okay, yeah. I forgot that you can actually just tab this. So yeah, tab, boom, boom, boom. There we go. So yeah, the H3O plus here would be a conjugate acid because it has received, and yes, if you actually just check from the other side, that yeah, H3O plus actually gives it to the I minus. So yeah, and then this one here would be the I minus, which would be the conjugate base, and so the pairing would be these two here. So yeah, the pairing is always um acid with conjugate base, and then base with conjugate acid. So yeah, it's just Hi with I minus, and then H2O with H3O plus. So yeah, there you go. Let's go and do part 2. Let's see if my Opera is turned on. Yep, there we go. Let me just change that to live chat. So yeah, nobody's here. Error. YouTube is not receiving enough video to maintain smooth stream as such view. Open widget. Okay. Let's hope. You know what? Let me just remove my Opera because I am scared that this stream would just by sudden get struck. And yeah, by the way, I am also recording this for an for an experiment as well. So yeah. I hope that that's fine. So yeah, let's do part 2. CH3COH, which is acetic acid, I believe it's called, and OH minus would result into CH3COO minus plus H2O. Okay, so the first thing first, that the CH. We only need to care about the we only need to care about the, what do you call it? The pair. So yeah, CH3COOH would pair up with CH3COO minus there. So yeah, basically the one that has the same thing would be paired up. That's the quick way to say it. So OH minus would connect to H2O. Part 3. That would mean that NH3 would pair up with NH4 plus, and then the H2O would pair up with H3O plus, no, OH minus. There we go. And then identify which of the following cannot be a Bronsted base and give a reason for your choice. H3O plus, it gives, so no. Because like yeah, Bronsted base literally means that you receive. And unfortunately H3O plus is not one of them. So yeah, unfortunately it cannot give. No, sorry. It cannot receive. So yeah, H3O plus is not one. H3O plus because if it receives unbalance, that's just basically how I see it. Part 2, uh, aluminum. I don't know what. Like yeah, I have already given up about how do you actually pronounce these things. AlCl4 minus. Um, yes. For AlCl4 minus, I would say um so no. Yeah. Um and yeah, by the way, H2O plus is just something that gives, which would make it an acid. For AlCl minus, it would be a base because it doesn't because it needs proton to be balanced. And then for Cn minus, the same. Base, it needs to be balanced. O2 minus, base, it needs to be balanced. Because like yeah, basically when you just put in H plus N, it should be balanced. And then after that, what is it? SiH4. Ooh, silicon. SiH4. Um, what happens if it actually be give? No, sorry. Does it give or does it give or does it receives? Mm, according to my mind, this guy would give. So no. Um, it gives. Well, yeah. Well, yeah. For me, it's just basically looking looking at the, what do you call it? Looking at its structure. So yeah. H4 is a strong bond. No, sorry. The SiH is a strong bond. No, is no. No. It gives because yeah. Too much proton unbalanced. And then lastly, as a ASH3, no, it gives too much proton unbalanced. So yeah, that's just basically a little bit on my theory, but yeah, I will let you just check back on all of the conceptual problems because I don't really actually have the expertise on chemistry, but yeah, I am just trying to help, just giving my mind to you, and I hope it's correct. C. Estimate the pH and pHO of a 0.03091 molars of hydroiodic acid. Um, hydroiodic. I believe that's HI. Ooh, but yes, the Ka here is 10 to the power of 9. So yeah, we can basically just ignore the thing because it's too big. So we can just know one thing about HI be- because of the thing is very big. It's 10 to the power of 9, which is very big. So we can just say that it's fully dissociated, which means that yeah, it would separate perfectly. So that means that we have 0.03091 molars of those, and so you just need to plug in into your calculator just to calculate the pH. So yeah, basically to calculate the pH, take the negative log of the answer, which is 0 point something. Where is it? 0.03091. 0.03091, yeah. And yeah, that would be the pH 1.51, which is equal to the pH. And then for the and then the POH or the PHO in this case, that would equal to 14 minus the thing, which would mean that would be 12.49. Yeah, 12.49. And there we go. That's the pH and the PHO. Pretty quick. Because like yeah, 10 to the power of 9, that is a pretty big Ka, which means that yeah, it would tend more to the right, which means that it would just almost fully dissociates. 17. Uh, bismuth's bismuth S3 dissolves in water according to the following reactions. Bi2S3 would result to 2Bi3 plus 3S2 minus. Okay. For which the solubility of product has the value 1.6 times 10 to the power negative 72 at room temperature. At 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 room temperature, how many Bi2S3 will dissolve in 3.091 times 10 to the power 6 liters of water? Ooh. Um, how many moles? That's that's the question. How many moles? Um, hmm. So yeah, basically that would mean. So yeah, we can just actually just write this first. The KSP would equal to the concentration of bismuth 3 plus squared and S2 minus cubed. Um, and so if we are talking about concentration, how many moles? Um, huh. Okay, so we can. Okay, so yeah, the first thing that yes, I'm gonna be actually assuming is that yeah, 1.6 times 10 to the power of negative 72 would equal to. I mean like yeah, it would just almost all of them would tend towards the to the left hand side. Um, like, yeah, we can just assume that, yeah, the concentration would be x. So that would be like 4 and 3x. Yeah, 4x times 3x. 4 times. No, 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 no. 4 times 27. Yeah, 4 times 27. That. That makes more sense. That would be 108. Yeah, yeah. 4 times 20. Yeah, yeah. That would be that many. X to the power 5. Um, what's the x? X the x is the x is something. Oh wow. Um, with this I can actually just find out how much of those. Oh, okay, okay. I mean, like, yeah, it's solvable because like when you have like, oh yeah. So basically, if you just put an x inside the thing, that would basically be the concentration of Bi2s3. So yeah, we can just try it out. 1.6 times 10 to the power of negative 72. Okay, that. Um, you divide it by 108. Oh wow, wow, that's a very big number. No, no, sorry, that is a very small number. Wow. Um, are you sure? Yeah. um, what I can do now is that I can actually take the fifth root of the answer, and that should give me the concentration. So yeah, that would be the constant. So yeah, x would equal to 1.71. Yeah, molars. No, times 10 to the power of negative 15 molars, and then you just need to multiply it by the volume, which in this case is 3.091. 3.09. So yeah, the answer multiply that by 3.091 times 10 to the power of 6. Um, it is still um. I mean, it is still viable. Well, yeah. So yeah, the amount here would be. So yeah, the amount of bismuth to S3 would equal to 5.299. Now 5.3 times 10 to the power of negative 9 moles. So yeah, that's that's the amount of moles. And how many Bi3 plus will be found in the solution described in part A? Um, if that would mean that I just need to multiply the thing by 2, just to get my answer. Which means that the Bi3 plus would equal to 1.05, no 1.06 times 10 to the power of negative 8 moles. But then the question is how many moles? So yeah, you can just multiply the thing by the mole, which is 6.02 times 10 to the power of 23. This would mean that the amount of Bi3 plus would equal to 6.38 times 10 to the power of 15. And yeah, this is why that I actually just read the question much more carefully. Because like, yeah, how many ions? That means that it's not moles, which is different. Because like, because a mole is just basically like it is like it is like a dozen, which is 12, and then I don't know anything else. Maybe like lucin, but yeah, I don't really know about those units. All I know is moles, which is just a very big number. So yeah, that's the amount of Bi3 plus that you have. Good. The final. Yes, this would be the final question. Oh, finally, I can just actually just rest a little bit on the practice problems. But yeah, I will let you just discuss a little bit on the quiz as well because I'm also gonna be taking the quiz. Yeah, because like yeah, because I am also just taking the course of 3.091. So yeah, let's just continue. Oh wait, actually, I have a phone here. Never mind. I didn't I didn't see it. So yeah. Let me just reduce the sound first. Oh, oh. So let's go to YouTube. And Joe Matt. There we go. Okay. There we go. So, strontium fluoride SRF2 has a KSP of value in water of 2.45 times 10 to the power of negative 9 at room temperature. Calculate the solubility of SRF2 in water. Express your units in units of molarity. Okay. Strontium fluoride. Okay. So, first thing, KSP would equal to the concentration of SR2 minus, no, 2 plus, yeah, and the concentration of F minus squared would equal to 2.45 times 10 to the power negative 9. Good. And so calculate the solubility of strontium fluoride in water. I will be assuming that this would be the maximum. So we can just assume that the SR is x. So yeah, that means that would equal to 4x cubed. Okay. So this would mean let me just put it into my calculator. 2.45 times 10 to the power of negative 9. Okay. And then you just divide it by 4. That would equal to 6.125 times. Oh wait, no, sorry. Let me just complete this straight away. So the answer, okay, yep. So the x would equal to 8.49 times 10 to the power of negative 4. And I believe that's the answer. Yeah, that many molars, which is the x is. So yeah, the x is basically the salt. And yeah, 8.49 times 10 to the power negative 4 is the answer. Calculate the solubility of SRF2 in 0.03 molars NaF. Express your answer in units of molarity. Assume that NaF is completely dissociated in water. Ooh. Wow. Huh. Wait, but that's the common ion effect. Yeah, that is basically the common ion effect. Oh, wow. So, I don't know what to do. uh, so yeah, that many would actually dissociate into those two. Ah, yeah. So, basically, the KSP would still be the same. Because from my assumption. Oh wait, no, sorry. Calculate the solubility. The solubility is the KSP, right? I think so. Uh, because like it actually fully dissociates. Hmm. Like, yeah, it doesn't give me like the volume. It it only gives me like the thing. What about if I assume that the thing is different? No, I cannot. Um, what I'm doing is that I'm just adding it. Um, 0.03, which would mean that it would dissociate to that. But then the fluoride would also react to the other fluoride. Assume that NaF completely dissociates in water. That would mean that the entire thing would actually dissociate into Na plus and F, and then the other guy would be Sr and F2, and then the entire thing would go crazy. Ah, hmm. Um, the solubility of SrF2. Oh wait, no, but yeah, that's the X, right? Doesn't that mean that all I need to do is to do the same thing? Because like yeah, the KSP would be yeah, the KSP will be the same. Yeah, we can use that fact because like yeah, that 2.5 times 10 to yeah, that number must equal to the concentration of Sr2 plus and the concentration of F minus. Uh, and yes, I think I just get myself too excited. Oh wow. Oh, okay. So assume that the thing has X. Yeah. So we can just assume that the concentration of Sr2 plus is X. Okay. And then you add them up. Oh, we can just assume that no, we cannot. Oh, how? The Sr2 plus. Express your answers in units of molarity. Um, we can use the fact. Does the concentration actually add up? Do concentrations actually add up though? Like yeah, that is actually a pretty critical question. Because if that's the case, and like yeah, it's something that it is something that you can try. Um, wow, this requires me a lot of thinking. The Sr2 plus, we can assume that that's X, and then we have 2X, but then you add it up by another 0.03, which would make the balance go off. Oh. This is like basically Le Chatelier's principle. From my mind, it is like Le Chatelier's principle. Um, is it just basically addition? No, because like yeah, because it requires some change. Have I actually done it in my book about the common ion effect? Hmm. Wow. Um. Mm, where is the compounding effect? Um. Oh wait. The CL will mess up the equilibrium. Um. According according to the one in my book. Oh. So the AgCl, which we have 1.3 times 10 to the negative 5 molars, um, would be multiplied by the minus x plus the point 1. Okay. I think I found how to actually do this. So yeah. So yeah, the KSP is the KSP will be the same, and then don't forget the Na plus and the, so yeah. The first thing is that the concentration of F minus that we'll have from that other concentration is 0.03 molars. And so we can just actually just find what KSP is. That would equal to the concentration. No. SRF2 would equal nope. And that should result into SR2 minus and F minus. Okay. Um. And then huh. Um. So we can just use ice. Yeah. So yeah. So yeah. First thing it is. So yeah. First thing it was solid, and then you have from the from the equilibrium from the ec it's 8.49, and then that's 8.49 plus that other concentration. We will assume that the volume is the same. Shh, nobody knows. And the result would be minus x and minus x. Okay, I guess. Oh, that NAF is already at the solution. So the SRF2 is just a solid that you put inside that liquid, which includes NAF. Oh my gosh. Jomat's brain just got exploded, man. So we can just find out what the X is. Can I? No. 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 No, I can. Wait, what? No, I can. So yeah, all we need to do is to try to find the X. Which unfortunately that I don't have the calculator to do it. Oh no. Oh wow. I need to get my calculator first. So stay right up as I'm gonna try to calculate this. And let me just mute me first. Okay, here we are back. Okay, here we go. So, yes, let me. So all we need to do is to just calculate the thing. Oh wait, no, it is cubic. What should I do? Um, there should be A, B, C, and D. Okay. So yeah, that's the fact. So that means that 8.49 minus x, and then you also have like 8.52, I guess. Yeah, 8.52. Oh no. Um. Uh. Yeah. Minus x. That means that means that the x means that means that one term would be cubed. Yep. So yeah, the a would be 1. For the b, what would the b be? What would the b be? Oh wow, the puns. One of them would be x squared because it would multiply by itself, but then it needs to be multiplied again by the thing. Oh no. Oh wait, no, sorry. The thing should be -1. No, wait. This 2.45 times 10 to the power of -9 must to equal to 8.49 minus x. Multiply the thing by 8.52 minus x. Okay. Squared. Um, you know what? I'll just put everything on. Oh wait, no, I cannot. Hmm. Well, yeah. I guess that's that. Previously I actually done that. Well, oh wait, I forgot. So yeah. So yeah. Oh wait, no. So yeah, basically this thing would be simpler. Yeah, this would be much more simpler. Wow. Why didn't I see that coming? So yeah, basically you have that, and then you need to multiply the thing x squared with the other guy, and then you need to add them up. Ah, wow. So yeah, let me just first plug it in. So 8.49. But what is 8.49? That's the cube root of 2.45 times 10 to the power of -9 plus the cage. Divide the thing by 4. Oh yeah. Close the cage. And then... Oh wait, that is 0.49. Good. And then you add it by... no, negative with negative, that's positive. Okay, so that's positive of 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 that number. Oh, I need to write this again. Shift 3 of 2.45 times 10 to the power of -9. Close it. Divide the thing by 4. Close the thing. Okay, that number. Add it by 0. Add it by 0.03 molars. But then this inner thing must be multiplied by 2 because of the crazy laws that I have. Oh my gosh. Oh wow. Multiply the thing by x. No, multiply by 2. 0.0625. I guess that should work. I hope so. But yes, by the way, that you can actually just use a graph just to find it. But yeah, I instead use I instead use my calculator because my scientific calculator is very cool. So yeah. Oh wow, this is gonna be very tiring for me too. Fine. C. Where's C? Where is C? Okay. 8.52 squared. Oh, that's the cube root of 2.45 times 10 to the power of negative 9. Close it. Divide the thing by 4. Close it. Uh, add it by 0.03. Put cages around it. Square the number. But that's negative. Oh no. But then, if that's negative, there should be another one. Uh, add it. Oh wow. That's positive. It would be negative. Like yeah, you can sense it from my expression. So yeah, it's 2 to the cube root of that 2.45 times 10 to the power of negative 9. There should be a multiply there. 10, yeah. 10 to the power of negative 9. Okay, close it. Times 10 to the power of negative 9. Close it. Divide the thing by 4. Close the entire thing. Wait. Wait. Oh, wait a minute. You know what? The best way is just by using a graphing calculator. Because like yeah, unfortunately my brain cannot actually handle this many variables, so yeah. I guess this is the only way. So cage them up. No wait, no. So yeah, first things first. X would equal to 2.45 times 10 to the power of negative 9. That number, divide the thing by 4. Divide the thing by 4. And then you take the entire thing. Raise it to the power of 1/3. There. Well, yeah. This thing could be X. This thing would be A. A would be that number, which is that. Yeah, precisely that. Perfect. And so, I just need to plug it in. Cage that in. Of 8.49. Subtract it by X. Wait, no. Sorry, that would be A. A subtracted by X. By A. Plus 0.03. Subtract the thing by X. You take the square. Subtract it by 2.45 times 10 to the power of negative 9, which I should have ignored. And so what's the answer? With my crazy zooming skills, I don't know. Why? Because I don't know how to calculate this. Wow. Well, yeah. I mean, like, there's like 3 intersects. Yeah, intersects. But I don't know which one to use. I should have taken the derivative. No. No. That didn't work. Oh yeah, I can actually just put this as this. X would equal to 0. Oh no. But yeah, somehow the value would be actually 0 point something. 0.8465. 8465. Which I am which I am hoping that it is the intercept. Well, yes, actually there's like, but yes, I am also a genius, so that means that I could find out what it is. Yes, it's 0.0008445. Wait, what? But the y? Wait, wait, what? I don't get it. What? Wait, what? Why? Wait, what? Why? Wait, what? Why? Unfortunately, my brain cannot actually handle this many things because there is another thing right over there that I really need to check. Is that touching? Oh, surely not. Yeah, it doesn't touch. Good. So that means that there's only one solution, and that's 0.00085. Finally, x would equal to 8.45 times 10 to the power of negative 4 molars. I finally done it. Even though that I just did something crazy that I should have not do, because I can actually just ignore something to be 0, so you can actually just plug in some other numbers in. But yeah, I guess that's the answer. Wow, that took me like a that that took me a while. So yeah, I guess that's I guess that's I guess that's life work of PPK. So yeah, I will later just actually gonna be rechecking this, and then later, before the quiz 9 life work, I will I will show you the mistakes if there are any. So yeah, thank you very much, and I will see you guys later.